Alright, so moving on to our next and final data structure, we have graph. So graphs are used on social networks. We also use graph on GPS. So basically we use anywhere where we need to model a relationship between many objects, like for example a router in a network or people. Actually, as a very interesting point, trees are a kind of graph, but we have cycles. Alright, so let's move on to graph property. The first one is that nodes are also called vertex. The line that connects each vertex is called edge. And there is no limitation on how many connections we can have for each vertex. And the final and the most important one is that when two nodes are connected, we say that they are adjacent or neighbors. In this example, you can see that edges have a direction, so we have a directed graph. When we don't have a direction on edges, we say that we have an undirected graph, like this example from here. So directed graphs are heavily used on social networks. Like for example on Twitter, you can follow someone on Twitter, like for example 0 is following 1, however 1 is not following 0. We can also have weights on edges, like this example from here. We use it to represent a strong connection between nodes, like for example on Facebook or social networks. We can increase this number if there is a lot of interaction between two nodes or two friends. So it's going to be very easy to calculate the best friends of a node. We can also use this kind of graph to calculate the shortest path between nodes, like for example the shortest path between 0 and 7, and we can use the weights in the edges, like for example the total cost of traveling or distance or probably traffic in order to calculate the shortest path. And we are going to see a very popular algorithm in order to solve this kind of problem in our coding interviews. Alright, so let's move on to the next point and let's talk about how we can represent in code a graph. So basically we have two main representations of graph in code. And the first one is the adjacency matrix representation of that graph, which is basically represents the rows and the columns as a nodes. We have 0 to 7 vertex. So in this case, we represent that as row and column. And then basically we represent an edge or connection between two nodes, just adding a 1 or 2 or Boolean value inside our two-dimensional matrix. In this case, for example, we can see that there is a connection between the node 1 and 0. If we go back to the logical representation, we can see that there is a connection from 1 to 0. We can represent that in our matrix adjacency list. However, between 0 and 1, there is no connection. So as you can see here, we don't set anything in our matrix. Let's take a look at this node from here. You can see that there is a connection between 6 and 5, and also there is a connection between 5 and 6. So let's take a look to our matrix to see how we can represent that. There is a connection between 6 and 5, and also between 5 and 6. So related to space complexity, you can imagine that this is going to increase exponentially when we need to add more vertices to our graph. So let me just put this from here and let me just add a quick note so you can see what the letter B and E represents. So as explained before, we having B equals B squared. This is basically because each time we need to add a new vertex, we need to add a new column and a new row, which means this is going to be quadratic. For example, if we need to add an edge in this scenario, it's going to be very straightforward because we can store the positions of the nodes in a hash table, and so we can access very quickly to the matrix by the indexes. So basically, if we need to add a connection between 2 and 1, it's going to be very easy because we can use the index of the matrix and just put a 1 in our matrix. So the time complexity is going to be B equals 1. Similarly to removing an edge, we only need to go to that specific indexes and you remove the true value from the connection. Querying an edge is basically the same as the previous one. We can access very quickly to the indexes in our matrix. Finding all the neighbors from a specific node is going to require B equals B, because if we want to get all the neighbors from the node 1, we need to iterate over the 7 nodes that we already have to see if there is a 1 there inside our matrix. So it's going to take us BOSB or the number of vertex that we have. Adding a node is going to take us BOSB squared because there is no such thing as a dynamic matrix. So basically you are going to need to copy the entire matrix that you currently have, create a new one, adding the new row and the column, and just duplicate that on the flights. It is very compute intensive adding a new node, and similarly removing a node from our matrix is going to be the same as the previous point, because for example, let's say that you need to remove the node number 4, that is going to be basically recreating a new matrix, and it's going to take BOSB squared, or the number of nodes that the graph have. I forgot to mention that all these calculations are done because we need to imagine the worst case scenario, and the worst case scenario is when we have a dense graph. So basically the definition of a dense graph is a graph in which the number of edges is close to the possible numbers of edges. That means, for example, that we have a connection between almost all the nodes in our graph. So you can imagine something like this, so we need to always think in the worst case scenario, where all the edges have connection with all the vertices. So probably using a matrix for representing our graph is going to be good if you know ahead of time that you don't need to add any node or removing any nodes. Otherwise, we can use the next representation method that we have for graph, which is the adjacency list. And I personally recommend to use this method on your coding interviews, otherwise you are asked to implement the matrix approach. However, using an adjacency list is going to be very straightforward to represent our graph, and it's going to be easily to understand how we can traverse a graph and how we can solve the different problems in our coding interviews. So if we go back to this graph example, we can see the adjacency matrix representation, and we can see also now the adjacency list representation for that graph. So guess what data structure we need to use for representing a graph with adjacency list? That's right, we need to use a dictionary or a hash table, where the key in our hash table is going to be the vertices or the nodes that we currently have, and the values for that hash table is going to be a list with all the neighbors that that node have. So let's take a look quickly to our logical representation here, and let's take a look to the node 0. So we can see that the vertex 0 is having a connection with the node 2. So if we go back to our adjacency list representation, we can see that it's having a connection with 2. So please ignore the number one in this example, just take into account that a box is represented as an item in our list. So let's take, for example, the vertex 6. We can see that 6 have a connection with 2, 5, and 7. So if we go back to our adjacency list representation and we move to the node 6, we can prove that we have a list with 2, 5, and 7. And total opposite to the node 6, we can see that the node 5 doesn't have any connection going out. So we say that this node is an island because it doesn't have any connection with other nodes. So if we take a look to the adjacency list, we can see that the node 5 doesn't have any list of neighbors. So let's go ahead now and discuss a little bit about the space and time complexity for the adjacency list, and let's see some examples. So if we go back to an example here, you can see that the space complexity that it's going to take is BOSB squared, because if we can imagine always the worst scenario is that we have a connection between all the nodes. We are going to have a hash map with all the nodes as keys, and as a value we are going to have a list of all the neighbors. So in the worst case scenario it's going to be B squared. So in the worst case scenario, which is a dense graph, we are going to have B squared, and this is basically the same as a matrix solution. Let's move on to the add edge operation. So let's say, for example, that we need to add a new connection from the node 1 to the node 5. So in this case we can get the list of neighbors in a OS1 operation. However, we need to iterate over this list in order to check if that edge already exists or no. So the time complexity is going to be BOSB, because again we need to think in the worst case scenario that is having connection between all the nodes. And comparing with the matrix approach, the matrix approach performs a little bit better in this scenario. So let's move on to the remove an egg. So in this case, we can access to the list of neighbors is BOS1. However, we need to iterate over this list in order to remove the connection from that list. So that we have BOSB. It's the same basically for querying an edge. It's basically checking if we have a connection, let's say between 1 and 5. So again, we can get the list of neighbors being BOS1. However, we need to iterate over this list in order to check if we have an edge or a connection between these two nodes. So it's going to take us B over B. Again, comparing with the matrix solution, the remove and the query is going to behave or perform a little bit better on the matrix approach. However, the find neighbors is going to be the same. That's basically because for finding out all the neighbors from a specific node, we are going to need to iterate over all the lists, find or get all the neighbors from that specific node. So it's going to take us B over B. Moving on to the next operation, adding a node is going to take us B over 1 or constant time, because basically adding a node is going to be very straightforward using a hash mat, as we can append new items to the dictionary or hash table in constant time, which is a big win if you compare with the matrix approach that is going to take us quadratic time. So in this case, the adjacency list is going to be a winner in this scenario. And the final operation, removing a node, is going to take us B over B squared, because when, let's say for example, we need to remove the node number 3, this is going to take us B over 1. However, we need to iterate over all the vertices that we currently have, and then we need to iterate over the list of neighbors that we currently have for that specific node to remove any connection if it already exists, or remove any edge that we have from that node. So that means that it's going to take us B over B squared or quadratic time. And if we compare that with the matrix approach, it's basically the same. So in summary, you can go with the matrix approach if you know the number of nodes ahead of time, or you don't need to add or remove any node in the future. Otherwise, in the majority of cases, representing the graph with that adjacency list is going to be more straightforward, and I highly recommend using this approach on your coding interviews, unless you are asked to implement the matrix approach. So in this course, we are going to use the adjacency list approach in order to create a graph class. Alright, let's go ahead now and discuss a very high level representation of how it's going to look our graph class. I was thinking that inside our graph class we could have a node subclass with a label string, and from there we are going to have the different methods that we are going to need: add node, remove node, that are going to just receive a string as parameter. Next we have the add edge methods, where we have the from and to nodes to add an edge to our graph. Similarly, we have the remove edge to remove an edge from our graph. And finally, we can have a very basic print graph functionality in our graphs class. Taking a closer look to this class and thinking on simplicity, because remember, on your coding reviews, we are always looking to save time. So let's say, for example, in the future, if we need to add something like the weights, like we discussed before, this could be anything like distance, traffic, or probably cost. So it's going to be very easy to add all this information in tuple. So we can remove this class from here and just handle the graph with a dictionary. So let's go ahead and just have an init method or a constructor in Python, where we are going to initialize only the graph to a dictionary. Because remember, our graph class is going to be an adjacency list. So let's go ahead now and implement this class in Python. So let's go ahead now and start creating our graph class. Let's define our init method, and here we can create our dictionary in order to represent our graph. Remember, on this dictionary, all the keys are going to be the nodes or vertices from our graph, and the values are going to be lists representing all the neighbors from this node. So we have VO1 time complexity for checking if a node exists in our graph, and also for adding new nodes to our graph. So that's awesome. So let's go ahead now and implement the add node functionality. So in this case, we receive a label, and remember, all the nodes, they need to be unique in a graph. So that's why we are representing this as a dictionary. So basically what we can do here is, before adding a node, we can probably check if the label already exists in our graph. If so, we don't need to do anything because it already exists. Otherwise, we can initialize our node in our dictionary. We can do something that sells as graph. In the position label is going to be equal to an empty list. Beautiful. We can collapse these two methods for now, and let's go ahead and implement the next one, that is going to be add edge. So in this case, we receive the from label and the to label, and added underscore here because these are reserved words in Python. So the first thing that we need to do in this method is checking that these two nodes already exist in our graph. And very similar to this validation, we need to do the same for the two nodes. I'm going to change this variable and this method. Awesome. These two validations are going to run in constant time for time complexity. So if we go back to our graph representation and let's imagine we need to add an edge from 1 to 6. This is going to be very straightforward because we are working with directed graph. We have a direction from and to. We only need to do something like self graph in the position from. We need to append a new neighbor is going to be 2. However, if we are working with undirected graph like in this scenario here, wherever we add a connection or add edge from 0 to 1 in this example, we also need to add that connection from 1 to 0. So basically we only need to do something like 2 and we need to append from. However, we only need to do this when we are working with undirected graph. So let me just add a comment. So currently we are working with directed graph. I'm going to comment this line out so we don't need to worry about it just yet. We are missing one validation where we need to check if the two node is already present in our adjacency list. I was reading a little bit about why instead of having an adjacency list, we don't have an adjacency set, for example, in order to handle the adjacency lists. So obviously in this case, we are using an array or a list in order to handle the adjacency list. But for simplicity in this example, we are using a list. So as you can learn a little bit more why we are using lists instead of sets. And you can learn more about a link that I'm going to drop here in the description of the graph class. So let me just add a very quick validation just to make sure that the two node is now added in our adjacency list. So in this case, what I'm going to do is override the adjacency list. So we just need to do a very quick validation, just checking that this node is not in our adjacency list. So that's why we have B equals B of the number of vertices for time complexity when we add an edge to our graph. Alright, so I think we have enough code to start testing our graph class. So I already created in a separate file a graph test Python file where we are just importing our graph class. So let me just go ahead and instantiate our class very quick. The first thing that we need to do is basically add a node. And next we can start adding our edges. We can go from 0 to 1. We can go from 0 to 2. We can go from 1 to 2. Let me just go ahead and print a statement and add the book stop here. So let me just debug this code and let's inspect what we have in our graph class. So in our graph class, we have the graph dictionary where we can see the adjacency list for each node. We have only 3 nodes. From the node 0, we can go to 1 and 2. From the node 1, we can go to 2. And from the node 2, we can go anywhere. So basically, the node 2 is going to be an island. Let me quickly test that we're raising an exception where we add an edge from a node that doesn't exist, which is correct. Alright, so let's move on to the remove node method. So let's go ahead and define our method and discuss a few steps before starting to code. So in this method, we are going to receive the labels node that we are going to remove. And here we can just discuss a little bit what we need to do on this method. So the first thing that we need to do is check if the node exists. Next, we need to remove the node from all the adjacency list. And next, we need to remove the node from our graph. And I think these are all the operations that we are going to need on this method. And in the end, we can discuss a little bit the time complexity from this operation. And let's implement the first step, that is checking if the node exists. Actually, you can also write an exception here if you want, but for simplicity, I'm going to just return null. Alright, so we are done with this step from here. Let's move on to the next one, and it's basically removing this node from all the adjacency lists from our graph. So let's go ahead and iterate over all the values from our graph. This variable is going to be a list, and we can use something like its label is in neighbors. We can basically say neighbors.remove and we can pass the label. And here we are done with the second step. Actually now for readability, I'm going to rename this variable to node. Yep, that looks better now. And let's go ahead and take a look to the next step. That is basically just removing the node from our graph. So in this case, we can use the pot method available for dictionaries on Python. And we only need to pass the key value that we want to remove. So in this case, it's going to be node. Awesome, with this line of code, we end all the logic related to removing a node from our graph. So let's go ahead and discuss the time complexity for this method. This validation from here is taking constant time. This for loop is taking BOSB because basically we are going through all the vertices in our graph, and next we trying to remove, or we are checking if that node exists in the neighbors of the adjacency list. So that means, remember, in the worst case scenario is we have a dense graph, we are going to have the same amount of nodes in our adjacency list. So basically we are looping 2 times, so we have time complexity of BO of B squared. And this line of code is taking us BO as 1 or constant time because we are removing an item from our dictionary. So remember, for time complexity, if we have separate process like in this example, we discard the ones that have the less impact. So in this case, these 2 processes from here have constant time, and so we take BO as B squared as the time complexity for the remove node functionality. Alright, so let's move on to our next method that is going to be the removed edge functionality. Here we receive 2 parameters, from and to, and let's go ahead and discuss what we need to do on this method. Similarly to our previous method, we need to check if the node exists. Next, we need to get the adjacency list from our front nodes. Next, we need to check if the 2 nodes exists on that adjacency list. And finally, just remove the 2 nodes is exist. Alright, so we only need to do 4 steps in order to implement the removed edge functionality. So let's go ahead and implement our first step, that is basically checking that both nodes exist. So in this case, instead of returning none or empty, we can just raise an exception in this scenario. So actually in this case, let's go ahead also and raise an exception when we're trying to remove a node that doesn't exist. Alright, so we are done with our first step here. So let's move on to the next one. In this case, we need to get the adjacency list from our front node. This is very easy. We only need to call our graph and just get the front nodes. Great, so we are done with the second step. Let's move on to the next one, that is basically checking if the 2 nodes exist. And this is basically just doing the validation and next removing that node from that list. So basically we can do something like, if the 2 node is in neighbor, here is where we need to remove that one. Awesome, I think we are done with the remove edge functionality. So let's go ahead and discuss the time complexity for this method. So in this tool validation from here, we are doing constant time because checking if an item exists in a dictionary is BO1. Here we are also getting something from our dictionary, so that also takes BO1 or constant time. And here we are iterating over our adjacency list. Remember, in this case, we always need to think in the worst case scenario or a dense graph. So the worst case scenario here is going to be BOSB, or the number of vertices or nodes that we have in our graph. The time complexity for this method is going to be BO of B. Let's go ahead and implement the print method for the graph. So that also is going to help us to validate that these 2 methods are working properly. So for this print functionality, what I'm going to do is very simply, I'm just going to loop through all the nodes from our graph, get the adjacency list from that node, and then basically just printing if there is something in that list. And we basically need to validate if we have neighbors on this node, and we can just print a debug message from here. So we can say something like, this node is connected with, and here we just concatenate all the items from the neighbors list. Also, we can potentially print that the node doesn't have any connections. So we can say here, node does not have connections. Great, this method looks good to me. So let's go ahead and just do a few tests for the remove node, remove edge, and print methods that we just recently add to our graph class. So if we go back to our graph test class, we already added a few nodes, 0, 1, and 2. And also we added a few edges. We add a connection from 0 to 1, 0 to 2, and 1 and 2. And we also raise an extension here. So let me just remove this line from here. And let me just try to see what we got in our print method. And let me run this functionality right away. This is basically because we are expecting to have a string instead of integer. So let's go ahead and transform that very quickly in our graph class. So go back to our print statement here. We need to somehow transform all the items inside this list into a string in order to be able to use this functionality from here. And we can do very easily that with the map function in Python, where we can say that map everything in this list to be a string. Alright, so let's go ahead and try again and see if this solves the problem. And boom, we have a very straightforward print functionality in our graph class. We are saying that 0 is connected with 1 at 2, which that's correct, and 1 is connected with 2. Alright, so let's go ahead and very quickly test first the remove node functionality. So after we print, we can say something like graph.remove node, and here we can remove 1. And let's go ahead and print something. Next, we can use this same functionality and see what we got. So if I run this code from here, we are getting another error. So basically we are raising an exception, and the only part where we raise an exception is when we validate, we need to say something like is node is not in. We need to raise this exception when the node doesn't exist. So let me go back to our test class and let me run this again. The node was printed correctly here, and then we remove 1. We printed again our graph, and 1 doesn't exist anymore. And beside that, also we remove the connection from all the other nodes. 0 has a connection with 1, and that was removed also. That means that the remove node functionality is working as expected. Let me just remove all the other nodes to see that we got an expected empty graph at the end. Let me run this bit again. We are removing all the nodes here, so we don't have anything to print. So that means that also the print functionality is working as expected. Alright, let's go ahead now and remove an edge. Okay, so let's say in this case we are removing from 0 to 2. We can use the remove edge, and we can say remove 0 to 2. And so let me just remove this bit from here, and let me print that again, and let's see what we got in this scenario. Alright, so we first print the graph, then we remove 0 to 2. 0 was connected to 1 and 2, and now it's just connected to 1, which is also correct. Let's see now what happens if I remove the other x that we have in 0, that is basically 0 to 1. And let me run that bit again, and the output is correct because 0 doesn't have connection anymore. Alright, so I think we are good with the insert and remove functionalities in our graph class. So let's move on to the next topic, that is how to traverse a graph class. Alright, so let's move on with graph traversal. So let me just open my nodes here at the beginning of my class, and let me just paste a few nodes that I currently have for traversing a graph. Previously we discussed traversing a tree, and as you can recall, we always start with the root node, and we can traverse this tree either using a depth first or breadth first. Remember, a tree is a kind of graph. So on graph we are also going to have depth first traversal and breadth first traversal. The main difference is that on graph we don't have a root node, so we can basically start from any node, and we can use also depth first traversal or breadth first traversal. Let's go ahead and discuss the depth first traversal first. So let me just change this example from here very quickly. Let's use this one. So on that first traversal, we always start visiting a node, so we need to choose one. So let's say, for example, we start on 1. So in these two algorithms, every time we visit a node, we need to keep track of them. So we usually store this in a set. In this case, let's go ahead and start on the node 1. We visit 1, so we need to store that in a data structure like a set. Next, we go deep in our graphs. That means that we are going first to 3. We assume that 3 was inserted first. This is why we store the adjacency list in a list or an array in our graph, because the order is very important, so we can have the output same as always. Because if you use a set, the order is not guaranteed using that data structure. Here we visit 3. Next, we check all the neighbors from 3, and we continue going deep in the graph. 3 only has one neighbor, which is 4, so we go ahead and visit 4. Next, we need to continue going deep in our graph. So in this case, we check all the neighbors from 4, but 4 doesn't have any neighbor, so the recursion ends here, and we go back in our recursion. So in this case, we are going to go back to 3. We don't have any other neighbors to visit on 3, so we also go back to 1. We haven't visited 4 from 1, but we already visited 4, so that means that we don't need to visit that neighbor anymore. So that's why we leave this in a gray color. And here we end the depth first traversal. And as you might already see, depending on which node we start or traversal, chances are that we don't visit nodes in our graph, and that's okay. So let's do another example. Let's say, for example, that we need to start on 0. let me just go ahead and start a did first search on 0. So basically we visited 0 because we start in 0, and in 0 we have 3 neighbors, 1, 2, and 3. Remember, in this example we are assuming that they are inserting in ascending order, so we go deep in our graph. We go to 1 because we assume that 1 was inserted first, and we mark it as visited, and we're starting to go deep from 1. So that means that 1 only has 2 neighbors. We need to visit 3 first because we go and continue going deep in our graph. So we visited 3, we mark it as visited, and we continue to go deep in our graph. 3 only has 1 neighbor, so we visited 4. We don't have any neighbors on this now, so basically we go back in our recursion and we go back to 3. 3 doesn't have any other neighbor to visit, so we go back to 1, and next we can go to 4. As you might remember, we visited 4 from 3, so we don't need to visit this node anymore. So that means that we can mark it as a gray line. We don't have any other neighbors to visit in 1, so we go back to 0 from our recursion stat, and next we haven't visited 3 and 2 from 0. So the next neighbor from 0 is going to be 2, so we go to 2 and we visit it. Next we continue going deep in our graph and we check all the neighbors in 2. And we only have 1 neighbor on this node, which is 4, but we already visited that node previously and we don't need to visit anymore, so we mark it as a gray line. So we don't have more neighbors on 2, so basically we go back in our recursion to 0, and we only have 1 node left to visit, which is going to be 3, but we already visited 3 from 1, so we don't need to visit this node anymore. And basically here we are going to end our did first traversal starting from 0. In this example, starting from 0, we were able to visit all the nodes in our graph, and that's it. We can do the did first traversal either using recursion or probably using an stat if you want to go with an iterative approach. So let's move on to the breadth first traversal. So the main difference between the did first traversal is that instead of going deeper in our graph, we use a queue. Basically, each time we visit a node in our graph, we need to add all the neighbors to a queue, because basically we need to visit all the neighbors first before going deep in the node. For example, if we start from 0, we need to visit first 1, 2, and 3. So basically we are going to do that, adding the nodes from each node that we visit to a queue. Let's take a look starting from 0 again, and let's go ahead and see what happened. Alright, so when we visited 0, we are going to have a queue with these 3 items, 1, 2, and 3. And we already marked all these nodes as visited. Alright, so we move on to the next stage, which is going to basically pop from our queue, and we can pop 1 from our queue. So in this case we move to 1. So we're starting to explore all the neighbors from 1, and 1 have 2 neighbors, 3 and 4. So we explore the node 3, but we already visited 3, so we don't need to add this node to the queue. We can ignore this node. So next we add 4. So we haven't visited 4 yet, so we add 4 to the queue. So in this case we just spot 1 from our queue and we add 4 to the end of the queue. So we don't have any other neighbors to visit or to add to the queue in this node, so we just spot from our queue. We put 2 and we move to that node. So we start to explore all the neighbors from this node, and the only neighbor that 2 have is 4, so we try to add 4 to our queue, but we already visited this node and 4 is already in the queue, so we can ignore that node for now. Great, so the next step is basically moving to our next item in the queue, that is going to be 3. So we're starting to explore all the neighbors from 3, and the only neighbor that 3 has is 4, but we already have that item in our queue, so we can ignore that node for now. Next, we pop our last item from our queue, which is going to be the 4 node. And we're trying to explore or find all the neighbors from 4. 4 doesn't have any neighbor, so our queue is empty and the algorithm ends here. Alright, let's go ahead and implement the depth first traversal algorithm. So remember, for traversing a graph, we are always going to require our start node, so we can receive that node as parameter. Let's go ahead now and briefly describe what we need to do on this method. So the first thing that we need to do is validate its node exists. The next thing is that we can use recursion for this case, and we need to keep track of the visited node with a set. We can pass this set to the recursive function. So let's go ahead and just implement these steps very quickly here. So the first step is validating if the node exists. It's saying is node not in self.graph. It's up to you if you want to write some exception, but for simplicity now, let's go ahead and just return null. The next thing is that we need to create a private recursive function, but first let's go ahead and create a set to keep track of the visited node. So we can call it visited, and we can initialize this into a set. Next, we can create a method similar to this name from here. So in this method, we need to send the node where we are going to start. And to keep track of the visited node, we can send visited. So let's go ahead and implement this method, and we can probably just collapse this method for now. So this recursive function is very similar to what we already did on trees when we do the pre-order traversal, because it's basically we need to print or visit the node wherever we visited, and then we go deep in our graph. So basically we print the node that we are currently are, and next we go deep in the graph using the neighbor from that specific node or the adjacency list. So in this case, the first thing that I'm going to do here is visit the node. Remember, for simplicity, we just visit the node, just printing the labels, rename this variable from here. And let me just put the node. And with this line, we are basically just visiting the node. And just to continue with the deep traversal of the tree, we need to basically call recursively this method for all the neighbors from this node. So in this case, we only need to visit the neighbor if we haven't visited yet. So as we are visiting the node here in these first lines, so we need to mark this node as visited. So we can do it basically using our set that we are currently passing in our recurse function. So we can add the current node to the visited set. That means that we already visited this node, and now we can validate if the neighbor is already visited. So we can say something is neighbor not in visited. We can say something like self that did traverse recursive, and we can send the neighbor, and we can also send our visited set. And that pretty much that's it. So the key point on this method is marking the node as visited. So on your coding interviews, this is probably something that your interviewer want to see, that you are marking a node as visited using a set, because remember, a set is giving us time complexity of constant time, where we need to add and wherever we need to check is there is something in that data structure. Awesome. So let's go ahead and test this functionality from our test class. So let me just quickly create a method, call it like test1, and we can just reset this from here. And let me just move all this functionality to this method from here. So we can just separate what we previously done in our previous lecture. So probably I can create another one here, define, let's call it test traversal. Let me just rename this method to main methods. And here we can probably test our traverse. All right, so I just recreated this graph over here using our graph class, and next I'm going to call the first traversal. So let me just collapse this method from here, and let me just call it here. So let me just run this function from here and see if we got any errors, and indeed we have an error here in line 144. So let me just take a look. This is basically because we are sending a list on this method when we call initially, and we only need to send the node. We don't need the adjacency list. So this was a bug that we can fix in our test. So let me just call our method again. So in this case, I'm going to traverse the graph from 1. So let me see what is the output on these methods. Let me just pass a parameter here, start, and we can use that start here. Let me collapse this bit and use for here. And let me just run this code again. Awesome. So in this case, we are visiting an island, so the output is going to be only 4. If we start from 2, let's see what is the output. It's going to be 2 and 4. That's correct. So let's go ahead and use test 0. Should be 0, 1, 3, 4, 2. That's correct. All right, let's go ahead now and implement the breadth first traversal. Similar to this first traversal, we need a start node, so we can pass that a parameter. And next, we can very quickly discuss what we need to do. The key point here is using a queue, validate this node exists, because we need validate is the start node 6. And next, we can use the queue to store all the neighbors. So basically, we need to say it is node in self.graph. We basically need to return or to write an exception, wherever you feel is better in this case. In Python, we can use the dec function in order to create a queue, and we only need to pass a list. So either you can do it by this or just passing an empty array. You can import this function from the collections module, so you can do something like this. So you can use the dec function from the collections module. So next, similarly to that first traversal, we need to keep track of the visited node, and the best data structure to do that kind of task is going to be our set. Next, as we already validating that the start node already exists, the first thing that we need to do is append that node to our queue so we can finish our algorithm that. So iterating over the queue basically consists in two steps. The first one is popping an item from the queue, and the next one is basically inserting new nodes to the queue. But remember, we need to validate before inserting a node to the queue if that node is already visited or not. So basically we are going until we have items in our queue. So we popped an item from our queue. We validate its current is in visited. If so, we can just continue popping item from our queue. Otherwise, if it's not visited yet, we can just visit, and we can do that with a print statement. And next, very important step in your coding interview, after you visit a node, you need to mark it as visited. This specific line is very important because if you forgot to add in your coding interview and you start debugging, sometimes it's hard to see that you forgot to add the visited item to the set, because it's not returning any error or anything like that. So it's very hard to debug. Remember, when you are working with graph in your coding interviews, have in mind that the most important thing in this kind of algorithm is always keeping track of the visited node. Otherwise, you are going to end in an infinite loop, or you are not going to have the output expected, and it's very hard to debug, trust me. And the final step is just looping from the neighbor from this node and just add these nodes to our queue only if they are not visited yet. So we need to say it is neighbor, not in visited. We can do something like queue.append, and we add that neighbor to our queue. Alright, this code looks good to me so far. Let's go ahead and add a few tests and see if we got the expected output and if we need to fix any errors. So let me just open this bit from here, and let me just comment this line from here. And let's go ahead and start with the most simple, probably the 1, 3, and 4. Let's go ahead and see if that's correct. So let's go ahead and just run a breadth first starting from 1. So basically we start from 1 to 3 to 4. That's correct. The breadth first is starting from 0, and let's see what we got in this case. So we got 0, 1, 3, 2, and 4. So if I start the breadth first traversal in 0, let's see what we got. 0, 1, 2. So we got something different here. We got 0, 1, 3. Let's go ahead and take a look why we are getting this output. Okay, here's the error. So basically, here is where I say that the other mothers, wherever you are inserting an edge. So basically, I'm inserting the 03 first and 02. So let's go ahead and move this bit to here. And that probably is going to help us to have the same output. So let me just go ahead and run this code over here. So we got 0, 1, 2, 3, 4. 0, 1, 3, 4. And that's pretty much it. So we got the same output using the breadth first traversal, and the breadth first traversal just made note that you need to use a queue. And remember, always mark your visited nodes either in breadth first traversal or depth first traversal. And that pretty much does it for graphs related to traversals. Alright, let's move on to the next topic related to graph, and is how can we determine if there is a cycle in our graph. So in this graph we don't have any cycle. However, let's take a look to another example like this one. And here we have a very clear example that there is a cycle in this graph. So our task here is going to be create a method that can determine if there is a cycle in our graph. So let's go ahead and implement this functionality. Alright, so let's go ahead and create a method kit has cycle. So we only need to return bool here, and let's pass this for now. Let's create a comment section here. Wherever you need to determine if there is a cycle in your graph, always think in the 3 sets approach. Okay, so we are going to have 3 main sets. One is going to be called all, the other one is going to be called visiting, and the last one is going to be called visited. Let's go ahead and run a very basic example of how this approach works. So if we go back to this example, let's go ahead and put all the nodes that we have. So we need to put from 0 to 7. Alright, so we start simply as doing a depth traversal to our graph. For simplicity, let's go ahead and start in 5. If we start on 5, basically we need to remove that node from our all set. and just move it to visiting. Alright, next step is, as we are doing a depth traversal, we need to go deep in our graph. The only neighbor from this node is 7. So we move on to the next node, and in this case it's going to be 7. So we move 7 to the visiting set. Awesome. So we continue to going deep in our graph. So we move on to the next neighbor from 7, and the only one is going to be 6. So we simply move 6 from all to the visiting node. We continue to going deep in our graph. So the only neighbor from 6 is 4. So we move on to 4. Sorry, I forgot to put 4 in the all set. So we move to 4. So in this case, we need to remove 4 from all and move on to visiting. Great. So we continue to going deep in our graph. So in this case, the only neighbor on 4 is 5. So basically, we need to move 5 to visiting. And here we found the key condition in order to find a cycle in our graph. If the node is in visiting, we have a cycle. So we have a cycle in this case. So you might wondering when we need to move to the visited set. So let's go ahead and take a look to our previous example where there is no cycle. So let me just change our example here, and let's move on to this one. And let's just do this example. So the nodes in this example go from 0 to 4. All right, so let me just remove all this node from here. And the only node that I'm going to need here is 4. Awesome. So let's go ahead and start in 1. So as we start in 1, we need to move from all to visiting in this example. We have 2 neighbors on 1. We assume that 3 was inserted first, so we go ahead and visit 3. So we move 3 to the visiting column. Next, we continue to going deep in our graph. So 3 only has 1 neighbor that is going to be 4, so we visit 4. 4 doesn't have any neighbors, so we just say that this node is already visited, so we move from visiting to visited. Next, we go back in a recursive call to 3. 3 doesn't have any more neighbors, so we move from visiting to visited. So we go back in a recursive call to 1, and in this case, there is 1 node left to visit, and it's going to be 4. However, 4 is not in our all set, but is in our visited set, so we can skip that node. That is another rule. Skip is node is in visited. We don't have more nodes to visit from 1, so we can move 1 to visited. Great, so we have 2 nodes left to visit, so we can move wherever we want in any order, but let's go ahead and just move 0 to visiting. 0 has 2 neighbors. Let's go ahead and visit 2 first, so we move 2 from all to visiting. 2 only has 1 neighbor, that is going to be 4, however 4 is already visited, so we move 2 to the visited set, and next we go back to 0. And in this case, the next neighbor in 0 is 3, however 3 is already in the visited column, so we can ignore that bit, and we are done with 0s, so we can move this node from visited to visited. So we are finished our algorithm here. That means that this graph doesn't have any cycle. Great, I hope it's clear. So let's go ahead and implement this functionality using the 3 sets approach. Great, so let me just collapse this bit from here, and let's go ahead and start our algorithm. So the first thing that I'm going to need is the all set. So we are going to create a set from cells that graph from all the keys that we currently have in our graph. Alright, so the next step is creating our visiting set, and similarly we need to do the same for visited. So our algorithm is going to finish when the all set is empty. So let's go ahead and do a while loop while we have items in all. And as a set doesn't have a method to pop an item from that, so let's go ahead and just create kind of a current variable here, and let's transform this into a list, and we are going to take the first element. Next, we need to check if there is a cycle, right? So we need to call a recursive function to do the depth first traversal. So let's go ahead and do something like has cycle, and here we can pass current, that is going to be our current node, and the 3 sets approach that I mentioned before, so we can pass it in this order. So if we have a cycle in this step, we can just return true. Otherwise, when we finish this while loop, we can say something like return false. Great, let's go ahead and implement this recursive method from here. The signature looks good, so let me just collapse this bit from here, and let's go ahead and implement the functionality right away. So the first thing that we need to do is moving from all to visiting. So we can do that very quickly doing all.remove. We need to remove current from all, and we need to add to visiting the same node. Next, we need to do the depth first traversal, and we can do that very quickly doing for neighbor. Here we need to validate the two conditions that I mentioned here. If the node is in visiting, we have a cycle, and obviously we need to skip the node is in visited. So let's do this one first. So we need to say if the neighbor is in visited, we can just continue. Otherwise, if the neighbor is in visiting, we have the cycle here, so we need to return true. Alright, so if we pass these two conditions, we can just continue with the that first traversal. Result is equal to self that has cycle, and again here we are going to pass the neighbor and all the three sets that we currently created, all visiting and visited. As long as we have a result in true in this scenario, we just need to return true. We can improve this a little bit just moving this code from here to here and remove this unused variable. So when we finish the that first traversal, remember we need to move from visiting to visited. Nothing happened here in this scenario, so we just need to return false. Awesome, I think we are done with this example. So we already have this example implemented here in this function. So let me just go ahead very quick and see if we got false from this function. So let me just call graph.hasCycle, and in this case I'm going to print the result in our console, or collapse this bit from here and run the code and see what we got. This is basically because I did a typo here. We need to put something like visiting that add, and we can pass current here. So we forgot to add the add method. So let's see if we got any other error. So let me just go ahead and run this code from here, and awesome, we got false, which is correct because in this example we don't have any cycle. So let me just go ahead and see if we can add a cycle easily from this example. If I add edge from 3 to 0, we are going to have a cycle between three nodes. So let me add another edge here from 3 to 0. So if we do that, we are inserting a cycle, and let me just go ahead and test, and the result should be true, and boom, we have a cycle in our graph and it's returning true, which is correct. Alright, for me these are the most important topics related to graph, and it's going to give you a really good base in order to solve any problems related to that. It will be good if you can research about topological sorting, so the hasCycle method is something that is going to help you on that algorithm. And remember the important point that I leave in a comment right here. Remember to uncomment this line is you need to work with undirected graph. The rest of the code is going to be pretty much the same. However, you need to remove, for example, an X here in this example. You also need to remove it from the 2 to the front, and not only from the front to the 2. A small thing that you need to take care is you are working with undirected graph. But I feel in the majority of cases in your coding interview, you are going to have a directed graph. So just take into account if you are working with undirected or directed graph, because this is very important, doing the basic operation on removing a node or removing an edge, and also obviously, and in this case, adding an edge to the graph.